All right, welcome back. In this lecture, we're going to continue where we left off from 3.1, and we're going to talk about one sample hypothesis testing on a mean. Just as a review, in 3.1, we developed a strategy for testing hypotheses generally, and we looked specifically at computing p-values for testing proportions. So the steps that we came up with for testing hypotheses were, first of all, to determine the null and alternative hypotheses, and then gather sample evidence, either p hat if you're testing proportions or x bar if you're testing means, as we are in this case. And then finally, to compute the p-value. The p-value is the probability of obtaining the sample results that we obtained if we assume that the null hypothesis is true. And the idea is that if the p-value is small, then that probably indicates that we were wrong to assume that the null hypothesis is true. And so a small p-value will lead us to reject the null hypothesis. And that's step 4, is to make a decision about whether to reject the null hypothesis. Basically, if our null hypothesis is less than alpha, we reject the null. And then finally, we write a conclusion about what our decision means for the alternative hypothesis. In this section, we'll discuss how to compute the p-value for hypothesis tests about the mean, and then we will also revisit hypothesis tests about the proportion, because one of the things we're going to do in this section is talk about a tool that we can use from artofstat.com to streamline the p-value calculation, because they can be sometimes a little bit tedious to compute. Okay, so let's get into it. Let's talk about the p-value for a one-sample mean test. Hypothesis testing helps us decide when we have sufficient evidence. For example, an agricultural chemical company believes that they have developed a fertilizer that causes corn stalks to grow taller. They test this fertilizer on 15 corn stalks of a certain variety whose mean height is 2.7 meters with a standard deviation of 0.5 meters. The fertilized corn stalks have a sample mean of 3.1 meters. Is this enough of a difference to say that the fertilizer is effective? So the corn stalks without the fertilizer, right, they grow to be 2.7 meters tall on average, but these corn stalks with the fertilizer grew to be 3.1 meters, which is larger, but is it enough of a difference to say that the fertilizer works, right? This is the kind of question that we want to be able to answer. The second scenario here says, on average, it takes a person 58 seconds to solve a particular kind of optical illusion, autostereographs. I don't know if you've ever seen those Magic Eye books, but they were really popular when I was a kid. Anyway, an elementary school teacher thinks that because children have good imaginations, they will be able to solve these illusions faster. To substantiate her hypothesis, she records the time it takes 30 students to solve an autostereogram. The mean was 55 seconds, and the standard deviation was 5 seconds. So once again, we see a difference. The question is this good enough evidence, right? Is this enough of a difference to say that her students are able to solve optical illusions faster than average? One way to answer these questions, right, of whether or not we have enough evidence, is to compute the probability of obtaining what was observed under the assumption that the null hypothesis is true, and that's what the p-value is. If the p-value is small, then we probably shouldn't assume that the null hypothesis is true, and so we reject it. But how do we compute the p-value when testing mean? In scenario 1, we can use what we know about the sampling distribution of x bar. So let's go ahead and do that. Let's compute the p-value for scenario 1. And again, as a reminder, the scenario is an agricultural company has a fertilizer. They think it grows corn stalks taller. They test it on 15 corn stalks that, without the fertilizer, have a mean height of 2.7 meters. And then with the fertilizer, they have a mean of 3.1 meters. So let's compute the probability of this happening by random chance if we assume that the null hypothesis is true. So first of all, we should probably state what our null and alternative hypotheses are, right? The null hypothesis here is that the fertilizer is not effective, right? The null hypothesis is always a statement of no change, no effect, right? And if the fertilizer is not effective, then the average height of our corn stalks would be 2.7, the same as it is for all the other corn stalks. The alternative hypothesis here is that the fertilizer works, so that the mean height of our corn stalks is going to be bigger than 2.7. And the sample evidence that we have is that our sample mean was 3.1. Okay, so we want to compute the probability of getting this if we assume that this is true, right? What's the probability of getting this just by random chance? Okay, so to do that, we know we want to compute a probability involving x bar, and we know how to do that, right? We can say, well, the probability that x bar is at least 3.1 well, we know that x bar is normally distributed, so we're going to use the normal calculator to do this, right? We're going to use normal dist. Mu sub x bar, right, the mean of our sample means is the same as the population mean, which we're assuming to be 2.7. So we would just use a mean of 2.7. And then the standard deviation is the population standard deviation, 0.5, divided by the square root of our sample size, 15. Right, so it would be 0.5 divided by square root of 15. We want the probability x bar is greater than or equal to 3.1. So our minimum is going to be 3.1, and our max will be infinity. Okay, let's see what we get. So we're going to use the normal dist with a mean of 2.7 and a standard deviation of 0.5 divided by square root of 15. Let's zoom in on that and find the probability. We want the probability that x bar is at least 3.1, since that's what we observed in our sample. It looks like that's a really small probability, right? 0.000, well, 0.0010 if we round to 4 decimal places. So 0.0010. Okay, and that's how we would compute the p-value for scenario 1. For scenario 2, on the other hand, and this is kind of a subtle difference, but you might notice that we don't quite have enough information to compute the p-value because we only have the sample standard deviation, not the population standard deviation. So again, here's the scenario in example 2. It says on average it takes 58 seconds to solve a particular kind of optical illusion, an autostereogram. So that's our population mean right there. We know that our population mean is 58. 58. An elementary school teacher thinks that because children have good imaginations, they'll be able to solve faster. To substantiate her hypothesis, she records the time it takes 30 students to solve an autostereogram. So our sample size is 30. The mean in her sample was 55, so sample mean was 55. And the standard deviation, again, in her sample was 5 seconds. So the sample standard deviation S was 5 seconds. But in order to use the normal distribution and compute the p-value this way, we need to know what the population standard deviation is. And that information was not given to us, right? The population standard deviation here is a big question mark. We don't know. And so we can't compute the p-value here the way that we did in scenario 1. In fact, situations like scenario 2 are actually much more common than situations like scenario 1. And so consequently, we need a way to handle those sorts of situations, and that's where students' t-distribution comes into play. So you may recall that students' t-distribution is defined as having this probability density function, which is crazy. Now, what we haven't talked about yet is that it turns out that if x bar and s are the mean and standard deviation of a sample size n taken from a population with mean mu, then this value right here, x bar minus mu divided by s over square root of n, follows student's t-distribution. This, by the way, if you squint at it hard enough, you might kind of recognize a z-score formula there. Remember that z is x minus mu over sigma. Well, in the case that we're looking for the z-score involving x bar, this would be x bar minus mu over sigma sub x bar. Sigma sub x bar is sigma divided by square root of n. Now, the only change here is that sigma is unknown, so we're not using sigma, we're using s instead. And so when we make that change, when we use the sample standard deviation rather than the population standard deviation, we get a value here that is not a z-score that follows the normal distribution, but instead is a t-score that follows student's t-distribution. What that means for us is that in order to compute probabilities, in order to compute p-values, like the one that we will need to compute for a scenario like this, which are by far the more common scenarios that we encounter, we're going to use student's t-distribution to do it. And so it'll be a two-step process. We'll first calculate this t-score that we've talked about, and then we will use the t-distribution in Desmos to calculate the appropriate probability. So let's do that for that second scenario. It says on average it takes 58 seconds to solve a particular kind of optical illusion. An elementary school teacher thinks that her children will do it faster. She gets 30 kids, and it takes them on average 55 seconds to solve the puzzles with a standard deviation of 5 seconds. Let's state the hypotheses to test her claim, and then we'll calculate the p-value. The null hypothesis here is that it's going to take her students as long as it takes any other people to solve the puzzle, right? That mu will equal 58, just like it does for everybody else. The alternative is that her students will be able to solve it faster, right? That the alternative is that this teacher is correct, right? That her students will solve it in less than 58 seconds. And the evidence that she has to support her claim is that she tried this out with 30 of her students and found that their average time was 55 seconds. The question is that a large enough difference for us to say for sure that her students are faster? Or is it possible that this is just kind of random chance that caused this? And so we have to compute the p-value. Now, in order to do that, we're first going to compute this value here, this t-score. We call it the test statistic sometimes. But the t-score is going to be x bar minus mu divided by s over the square root of n. X bar in this situation we've already written down was 55. Mu we're assuming to be 58. Our sample standard deviation was 5. And our sample size n was 30. Okay, 30. So let's see about how much that is. You can go ahead and punch this into your calculator. 55 minus 58 divided by 5 over square root of 30 comes out to about negative 3.29 approximately. And now we will use student's t-distribution to calculate this probability. So we're going to go to Desmos, and then we're going to go to t-dist. And when we use the t-distribution in Desmos, remember that we put in the degrees of freedom into the parentheses. The degrees of freedom is always one less than our sample size. And since our sample size here is 30, the degrees of freedom will be 29. Okay? We want the probability that x bar is 55 or less, okay? Because this is a left-tailed test, okay? So we have a less than or equal to 55, and so that's equivalent to the probability that t is less than negative 3.29, because that's the value that t-score that we just computed. Okay, so in the t-distribution, since we're looking for the probability that t is less than 0.329, I think for our, we're not going to have a minimum. We'll just say it goes to negative infinity, and for our maximum, we'll use negative 3.29. This is our p-value, by the way. Okay, let's see what we get. So we want the t-distribution with 29 degrees of freedom, negative 3.29. Zoom in on it, find the cumulative probability, and we want negative 3.29. Okay, so that's a pretty small probability also. That's 0.0013-ish. You can see if you zoom in, right, it is highlighting that amount. Okay, 0.0031. Okay. So that's how we would compute the p-value on a situation like this where we don't know what the population standard deviation is, which is most of the time the case. As you can see, this process is somewhat tedious, and you can imagine that it would be even worse if you had raw data. Because notice that in this problem, the values here were already summarized for us, right? Somebody computed the sample mean for us already. Somebody computed the standard deviation for us already. If we just had raw data, we would have to compute those values before we could plug them into this formula right here. And so that would be quite a tedious process. So let's learn how to use technology to do this calculation for us, to compute the p-value for us. So what we're going to do is we're actually going to use a whole bunch of different calculators in this website called artofstat.com. So you can either go to artofstat.com and then navigate to inference for a mean, or you can follow this other link, istats.shinyapps.io/inference_mean, and get there directly. That's what I'm going to do. Now, under Enter Data, you're going to choose Summary Statistics if you just have a summary of the data like we had in example 1. Or you're going to choose your own if you have raw data, in which case you'll need to enter the raw data into the observations box. You can copy and paste any raw data from Excel. So if you have an Excel workbook to work with, you can just copy and paste. In fact, for this lecture, if you haven't found it already, there should be an Excel workbook with this lecture on Canvas that you can download, and then any problems where we're working with a raw data set, you can just copy and paste the data from Excel into this calculator. Or you could type them in manually yourself, right? You could also just do that. And then finally, under type of inference, you're going to choose significance test, and then you'll enter the null and alternative hypotheses, and the calculator will do the rest for us. So let's take a look at an example, or a couple examples, right? So number 2 here says, a student read that in 2020, the average cost of a 2-bedroom apartment in Visalia was $1,275 per month. She suspects that price has gone up. To test her hypothesis, she randomly selected 16 apartment complexes and found that they charge an average of $1,300 per month, with a standard deviation of $23 per month. At the 0.05 level of significance, is the student's suspicion substantiated? Okay, assume that apartment prices are normally distributed. Okay. We'll talk about why that's important later. But okay, so let's run this test, right? Step 1 in our hypothesis testing procedure is to state the null and alternative hypotheses. The null hypothesis is that prices have not changed since 2020, right? The average cost of a two-bedroom apartment is still $1,275 per month. Okay? The alternative is that this student is correct, right? That prices have gone up, right? That the average price of a two-bedroom apartment is now more than $1,275 per month. Step 2 is to state the sample evidence we have in favor of the alternative hypothesis. And the evidence is that, well, she collected a sample of apartment complexes and found that they had an average rent of $1,300 per month, which is larger than $1,275. The question is it a big enough difference for us to for sure say that, yes, this student's suspicion is substantiated? Well, to answer that question, we have to compute the p-value, right? And so this is where we're going to go to artofstat.com. And we want to use that calculator. So let's go to, let's follow this link. Okay, so this is what it looks like when you follow the link. By the way, I should mention that if you want to download the app onto your phone or your tablet or something, you can do that. I'm just going to use the web app, so I'm going to say dismiss. And then we get here. Now, I want to use summary statistics, so I'm going to choose summary statistics. And I can enter the variable name here. We're looking at apartment prices, so that's what I'll call it. Whoops. Apartment prices. Our sample size was 16, right? She sampled 16 apartment complexes. She found that on average they had a rent of $1,300 per month, and the standard deviation was $23 per month. Now, we don't want to get a confidence interval. We'll talk about those in the next section. For now, we just want to run a hypothesis test. In our hypothesis test, the null hypothesis is that the mean is still 1275, okay? And we don't want to run a two-sided hypothesis test. We want a, we think that the price has gone up. We think the price is greater than 1275 per month. And you can see that you get all kinds of good results here, right? You're given, they give you a little chart. They give you the test statistic, right? They show you the where the t-score falls in students' t-distribution. So it's all really nice. The most important one, of course, is the p-value, which is in that third box at the very right-hand side, right, where it says p-value 0.0003. Right, so this value right here. Okay, so let's write that down. I would like for you to show your work on these problems by showing me what you entered into artofstat.com. We entered a mean of 1,300, a standard deviation of 23, and a sample size of 16, okay? And then, of course, we entered these hypotheses as well, but you've already written that down, so you don't have to write it down again. The p-value that artofstat spit out for us was 0.0003. So I can use that to make my decision. The level of significance we're using here is 0.05. 0.0003 is far less than 0.05, so we reject H null. And then finally, we can write out a conclusion. Okay, so our conclusion should say something like, there is sufficient evidence, right? We're rejecting the null hypothesis. We're rejecting the null hypothesis in favor of the alternative. So we'd say there is sufficient evidence to indicate that the mean price of a 2-bedroom apartment has increased, right? Okay, so that's how that would look. Let's look at one where we have raw data, like in number 3. It says, according to the United States Mint, quarters weigh 5.69 grams. A researcher is interested in determining whether the state quarters have a weight that is greater than 5.6. I think it meant 5.69 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. Test his claim at the 0.05 level of significance. Okay, so same idea, right? The null hypothesis is that the average weight of the state quarters is 5.69, the same as it is for any other quarter. The alternative hypothesis is that he thinks that they weigh more than that, right? So the alternative is that mu is greater than 5.69. So that's step 1 in our procedure. Now step 2 is to gather the sample evidence. And here we weren't told what the sample mean was. We were just given the sample data, okay? So we can enter that into our calculator to figure out what that is. Or since you have this data in Excel, I'm not going to show this to you, but since you have it in Excel, you could just use the equals average function in Excel to figure out what the average of this data set is. Okay? But you should get the same thing if you just plug this directly into the calculator. So let's go over to that calculator. That's what we're going to want to do in step 3 anyway, is to use the calculator at art of stat. And this time we just have raw data, so we don't really have any work to show as in terms of what we're feeding into art of stat. So we'll just write down what we get for the p-value once we go there. Okay, let's head over to art of stat. So what you're going to want to do at art of stat is click on your own, and that'll give us a way to enter our own data. I'm going to name this weights of quarters. Okay, and then you can either type your observations in with a space or a comma between them, or you can just copy and paste from the Excel spreadsheet. So I'm going to enter this data set. So I'm going to pause this, and when you come back, the data will be in. Okay, so I think I have all of the data in there correctly. And then under type of inference, you're going to say significance test, of course. Our null hypothesis is that mu equals 5.69. And the alternative is that this is greater. Okay. So this time you can see that we got a t-score that was pretty close to 0, right? The corresponding probability is like 15%, right? That's our p-value here. You can also see it makes a nice little box plot and a dot plot and stuff. So those are kind of fun. Anyway, but yeah, it looks like we don't have sufficient evidence to say that the state quarters weigh more, right? Our p-value is too large. So let's write down our p-value, 0.1555. Oh yeah, our sample mean, I almost forgot. Our sample mean is 5.702, right? That's given right there, and the standard deviation is also given in case you need it. But the sample mean is 5.702. So the mean was 5.702. So that is a little bit larger than 5.69, but not very much. And in fact, the p-value is pretty large, 0.1555. So (1.1) or 0.1555 is not less than our level of significance, 0.05. So we do not reject H null. Okay, there. In other words, right? There's like if we assume that H null is true, then there's still like a 15% chance of observing this sample mean, which is not a low probability by any stretch of the imagination. So there's no reason to reject the null. And since we're not rejecting the null, we would say there isn't sufficient evidence to support the alternative, right? That's what we would say in conclusion. There is not sufficient evidence to conclude that the state quarters weigh more than the standard quarters. By the way, some of you may be, most of you probably, come to think of it, are not old enough to remember that. So when I say state quarters, I mean the quarters that have special designs on the back for each state in the country. It used to be that all of the quarters were just the standard quarters with the eagle on the back. But around the year 2000, they started to release special state quarters for each of the states. And this actually kind of caused a little bit of a problem with vending machines and stuff because the weights were a little bit off. So they kind of had to recalibrate some of the machines and everything. Anyway, kind of an interesting thing. My question is, okay, so the researcher doesn't have good enough evidence here, but they only looked at 18 state quarters. Why didn't they just look at all 50 of them? That's what I would have done. But anyway, that's how that works, okay? So you can do this whether you have a summary of the data like we did in example 2, or you can do this with the raw data like we did in example 3. Now, this sort of begs the question, well, why are we doing the p-value the hard way on one sample proportion testing when we can just use these apps for the one sample mean test? And the answer to that question is, well, actually we could use, there's an app for both, right? So you could also use an app for the one sample proportion test, and that's what I'm going to ask you to do moving forward, okay? My purpose in the previous section with making you do it by hand is to get you to really understand what the p-value is measuring. But moving forward, I think we'll just use these apps to compute the p-value for us. So it's a similar set of, of instructions for computing the p-value using the apps. Let's just look at a couple examples. So number 4 here says, a headline read, more than half of Americans say federal tax is too high. The headline was based on a random sample of 1,026 adult Americans, in which 534 stated that the federal tax they have to pay is too high. Is the headline accurate? Is the headline accurate? Well, let's see. The null hypothesis is that it's not accurate, right? That the proportion of people who say that that federal taxes are too high is not more than 50%, not more than half, that it's only equal to half, okay? And then the alternative is that it is more than half. The sample evidence in this case, since we're testing a proportion, would be the sample proportion, p hat. Okay, and it looks like there were 534 people who said taxes were too high out of 1,026 people surveyed. And you can punch that into your calculator to see how much that is. It looks like about 52%. 520. Okay, that is more than 50%. It's not that much more than 50%, but it is slightly more. Well, let's compute the p-value. So I'm going to use the art of stat calculator. I'm going to put in, okay, maybe I should take you there to see what it looks like first. Let's just head over to that calculator. So let's follow that link. Dismiss. You could, download the app or whatever. I'm going to do number of successes. That's where we're going to put in our sample evidence. Our sample size on this example was 1,026. And the number of successes was 534. And I don't want a confidence interval. I want a significance test. And for the null value, for my null hypothesis, it was that the population proportion would be exactly half, right? 50%. 50%. And I didn't want a two-sided one because I wanted to test whether the headline was accurate. In other words, I want to know if more than 50% of people feel this way. Okay, so these are the results I would get. I've got a pretty large p-value here, 0.0949. Okay. All right, so let's write some stuff down. 0.0949 was our p-value. We put in the number of successes, x, which was 534. We put in the sample size, n, which was 1,026. And then we got a p-value. I've already forgotten it. It was 0.0949. Okay. Well, 0.0949 is not less than 0.05. So we do not reject H null. Okay? So then our conclusion would say something like, there's not sufficient evidence, right? There's not sufficient evidence to indicate, or to, maybe it would be better to say there's not sufficient evidence to support the claim in the headline, right? And then maybe we could clarify the claim was that more than half of Americans say taxes are too high, right? Okay. It is interesting to note that our sample proportion was 52%. That's more than 50%, right? But it wasn't different enough for us to say for sure that the majority of Americans feel this way, right? We would need a larger sample size, I think, to make that declaration. And even then, there's only like a 2% difference between this and that, right? So it's just not that substantial. Okay, one more. You should definitely pause the video, work this one out. It says a researcher who is trying the effects of, or is studying the effects of income levels on breastfeeding of infants hypothesizes that countries where the income level is lower have a higher rate of infant breastfeeding than higher income countries. In what the World Bank classifies as high income countries, 22% of all babies are breastfed. A sample of 500 babies in what the World Bank classifies as low income countries was taken, and researchers recorded whether or not the babies were breastfed. And here I think it will be useful for you to use the data in the Excel workbook, because otherwise you're going to be having to type in a whole bunch of words into the calculator. But it says at the 5% level of significance, does this show that low-income countries have a higher incidence of breastfeeding? So I'll let you pause the video and see if you can work that out, state the hypotheses and the whole 9 yards. Okay, here's my solution. So the null hypothesis would be that low-income countries have the same breastfeeding rate as high-income countries, right? That P equals 22%. The alternative is that the researcher is correct, that the proportion of women who breastfeed is higher in low-income countries. She thinks it's higher. Okay. Oh, I don't know why I labeled that 2. That's just our alternative hypothesis. Step 2 would be to collect the sample proportions here. So we want the sample proportion of low-income babies who are breastfed. So here, I think it would be useful to go ahead and put the raw data into the calculator and then calculate this value. So let's head over to the calculator and do that. Okay, so I've got all the data in here, and if you're like me and you copied and pasted the entire column, then the column title, breastfed, was also included, and that needs to not be in there, so go ahead and delete that. Okay. And now BF stands for breastfed, NBF stands for not breastfed. We want the proportion of children who were breastfed, so we're going to choose BF as the category that defines success, right? So it's not going to be NBF, it's going to be BF. And again, we don't want a confidence interval, we want a significance test. The null hypothesis was that 22% of babies would be breastfed in the low-income countries. And we wanted to run this as a right-tailed test, right? We thought that more than 22% of babies would be breastfed in the low-income countries. Okay. It looks like our sample proportion, by the way, was 25%. This program automatically counts up all the BFs and NBFs, right? It says that there were 500 in the sample in total and 125 successes. So sample proportion 125 out of 500 is 25%. And the test statistic, the p-value is what we're really after. The p-value 0.0527. So not quite good enough evidence, but it's really close. Okay, so our sample proportion is 25%. Our p-value is 0.0527. Okay, so our p-value is, or actually it's exactly equal to 25%. I was going to say it's approximately 25%, but it's equal to 25%. To get the p-value, we went to art of stat, and we got a p-value of 0.0527, I believe it was. Yeah, 0.0527. Okay. At the 5% level of significance, in other words, alpha equals 0.05, right? This isn't quite good enough. It's really close, but we're not going to reject the null. 0.0527 is not less than 0.05, so we do not reject H null. Okay. And so once again, we would say there's not sufficient evidence, right? There is not sufficient evidence to say that low-income countries have a higher breastfeeding rate than high-income countries. And once again, I think that's kind of interesting because our sample proportion was larger than 22%, but it wasn't enough of a difference. Either it wasn't enough of a difference or we didn't have a large enough sample size, or potentially both, right, in order for us to conclusively say that yes, low-income countries have a higher breastfeeding rate. But anyway, that will do it for this section. So in the next section, we'll talk about confidence intervals and what confidence intervals are used for when we're performing inference. Until then, have a good one.